Hi viewers, welcome to LMS Solution. Today we are going to see about grid connected PV battery system. This is a simulation model we developed for a grid connected PV battery system. This system consists of solar PV array along with boost converter, and then battery along with the bidirectional converter, and then it have grid connected full bridge inverter, and then it have grid. So first we have to see about that the solar PV system. So the solar PV rated at 250 watts. That means single panel is rated at 250 watts and the voltage at maximum power point is 30.7 volt and current at maximum power point is 8.15 amps. Here we are using 4 panel in series. So totally it can generate maximum of 1000 watts at a standard test condition. That means 1000 watts per meter square under 25 degrees Celsius. If irradiation equal to 1000 watts per meter square and temperature equal to 25 degrees Celsius, then it can generate of a peak power of 1000 watts. So when you click that plot, you can see the variation of IV and the PV characteristics. So here you see that when the radiation is 1000 watts per meter square, it generates around 1000.82 watts. When the irradiation is 800 watts per meter square, it will be generated around 800. When irradiation equal to 600 watts per meter square, it will be generated around 598.861 watts. And then when irradiation equal to 400 kilowatt 400 watts per meter square, it will be generated around 396.1 watts. This is a peak point. We need to extract nearer to that peak point. For that only we are using MPPT algorithm. So here we are using incremental conductance MPPT along with this boost converter to extract the maximum power, try to extract the maximum power nearer to that peak power point. So for that we are measuring the PV quantity. So here we are measuring the PV quantity like voltage and current. So it will be processed inside the incremental conductance MPPT. So when you click inside, so you will see that this is a code for incremental conductance MPPT. Here we are measuring that voltage and current of the PV, and here we are fixing the 4 parameter initial duty cycle, maximum minimum duty cycle, and then here we are fixing the increment decrement duty cycle value, and here we are fixing that initial value for a previous instant voltage, power, current and the duty cycle, and then here we are calculating the power. Here we are calculating the difference between current and previous instant voltage. So difference between current power and the previous instant power, the difference between current amps and the previous instant amps. And then here we are checking the first 3 setup condition. We are checking dV equal to 0 and dA equal to 0. Both will be 0. You have to keep the duty cycle equal to previous duty cycle. That means already system operated at a maximum power point condition. So next, if suppose dA equal to greater than 0, then we need to decrement the duty cycle. Otherwise, we need to increment the duty cycle. So this is the first 3 setup condition you need to check for incremental conductance. So next you have to check the another 3 setup condition. I think but dA by dV. So next you have to check the dA by dV equal to minus IVB. This is known as the incremental conductance condition. So if it is equal, both are equal, dA by dV equal to minus IVB, then the system already operate in the maximum power point. That means PV is already operate in the maximum power point condition. Here we need to keep that the duty cycle is equal to previous instant duty cycle. If dI by dV is greater than minus IVB, then we need to decrement the duty cycle. Otherwise, we need to increment the duty. By using this condition, you have to calculate the duty cycle. Next, you have to check the duty cycle with the maximum minimum value. If D is more than D max or D is less than D minimum, then we need to keep that duty cycle equal to D volt. Otherwise, you have to allow this duty cycle to further process. So next, after here we are overwriting that the current instant value with the previous instant. This code will be keep on executing for every sample time. Then it will be calculate the duty cycle every sample time. Then it will be processed via generator. It will be generate the pulse. This pulse will be given to boost converter. So here we are giving that the pulse from the BWM generator, and it will be extract the maximum power from the PV array and also boost the voltage from 120 to 220 volt. And here we have local load. So next it comes to battery. So here we have battery. The battery is rated at 48 volt. Rated capacity is 50 Ah, and then initial state of charge will be 50%. So here we have a converter. So this bidirectional converter is controlled by means of a voltage control method. Why we need to control with the voltage control method means the PV and the battery both are connected in the common DC bus, boost converter and bidirectional converter. So we need strong DC bus, then only we can exchange the power between PV to battery, PV to grid side, PV to load side. So we need to maintain DC bus constant always. For that only that the bidirectional converter is controlled by means of voltage control method. For that we are going to measure this DC-link voltage. So that will be compared with the reference voltage. Reference voltage will be 225. After comparison, the error voltage will be processed by a PA controller, and then it will be generated the duty cycle. The duty cycle will be processed by a prelude generator, and it will be generated the pulse. So you have two pulse. One is direct pulse, and another one is complement pulse. So this pulse will be used to control these two IGBT of the bidirectional converter. And then this bidirectional converter, another use will be it allow that current powerful in the both direction. When charging mode, it allows the current from this from DC bus to battery side. When battery in discharging mode, it will be transfer the power from, that means it allow the current flow from battery to DC link according with the power balance in this system. If suppose the battery, that means PV having excess power, surplus power, then it battery going for charging mode. If PV is not having surplus power, system having deficit power, that means it needs some demand supply, then battery will be going for discharging mode. So next to move on to inverters. Here we have inverter, and then here we are measuring the inverter current, and here we are measuring the inverter voltage. First we need to that means here this inverter will be controlled by means a current control method. We have to allocate the some current, that means contracted current, how much current we are going to send to the grid point. For that we have to generate the reference current. First you have to fix the I reference value. I reference will be 3 amps peak. That should be converted into sinusoidal forms. For that we have to use PLL, the voltage, right, voltage of the grid side, that will be converted into sine cosine form, and then this kind sine cosine will be multiplied with this reference current, and then here we are applying that Clark transformation. After applying Clark transformation, it will be converted into alpha and beta reference. This is alpha beta reference for the controlling purpose. Next, here we are measuring the IA current, that means inverter current. The inverter current can convert it into alpha beta by using Clark transformation. So now we are having alpha beta in the actual value and the alpha beta in the reference value. Then the both will be actual and reference will be compared here, and then processed via PA controller. This will be generate the control signal. So this control signal again it will be converted into AB form by using inverse Clark transformation, and finally you take only A quantity. A quantity will be processed via pendulum generator. Here we are using sinusoidal pendulum generator. The sinusoidal pendulum generator will be generate the pulse. This pulse will be control this full bridge inverter. According with that current reference, this inverter will be send the power from the DC link to grid side. And here we have the local load, AC load, and here we have grid. Grid is rated at 110 volt RMS and 50 Hz. So here we are going to test the system by changing the radiation. So here you see that, right, we are changing the radiation from 1000 to 500 and 500 to again 1000. We can change to 1000, and then we'll check the result, how the system is working when changing from 1000 to 500, 500 to 1000. So here I'm going to change to 0.9. Let me run the simulation, and then you have to check the different results. Battery, once again, battery, PV. Here seeing that PV voltage, DC bus voltage, PV current, and the boost converter current. Here we have PV and boost converter power, and this is battery voltage and current, and here you can see the state of charge of battery, and here you see the inverter voltage and the inverter current and grid current. Just I'm going to run the simulation. This inverter voltage is maintained around 110 volt RMS. Here you see the PV voltage maintained around 120 volt, and DC bus voltage maintained around 225 volt, and then current is maintained around 6 amps PV current, and boost converter current is maintained around 3 amps. So here is the PV power is around 800 watts. Because of incremental conductance MPPT is not able to extract the maximum power, but it extracting around 80%. So when the irradiation is changed to 500 watts per meter square, it will becomes around to 400. That means the incremental conductance MPPT can extract only 80% of efficiency. MPPT efficiency ratio will be only 80% in the incremental conductance MPPT. During that power reduction in the PV power, that means due to the irradiation reduction. So what will be happen? Initially battery going for charging mode. After that it going for discharging mode. Initially current will be negative, and after 0.3 second current will be positive. And also here you see that initially it will be in charging mode. After 0.3 second it will be discharging mode. Again it will be changed to charging mode, because the PV power increased from around 400 to 800 again. So here you see that this is inverter voltage, and this inverter current is grid current. So this inverter current, whatever current we are fixing reference current, that current will be, once again, so here you see that 3 amps current will be sent to the grid point. So this is a working of this model, that means grid connected PV battery system with the incremental conductance MPPT in MATLAB simulation. So thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you so much. Bye bye.